In Part 4 of Lecture 7, we will discuss paging and segmentation. Both unequal fixed size and variable size partitions are inefficient in the use of memory. The former results in internal fragmentation, the latter in external fragmentation. Suppose, however, that main memory is partitioned into equal fixed size chunks that are relatively small, and that each process is also divided into small fixed size chunks of the same size. Then the chunks of a process known as pages could be assigned to available chunks of memory known as frames or page frames. We show here in this part of the video lecture that the wasted space in memory for each process is due to internal fragmentation, consisting of only a fraction of the last page of a process. There is no external fragmentation. The figure on the slide illustrates the use of pages and frames. At a given point in time, some of the frames in memory are in use, and some are free. A list of free frames is maintained by the operating system. Process A, stored on disk, consists of 4 pages. When it is time to load this process, the operating system finds 4 free frames and loads the 4 pages of process A into the 4 frames, as you can see here in figure B. Process B, consisting of 3 pages, and process C, consisting of 4 pages, are subsequently loaded. Then process B is suspended and is swapped out of main memory. Later, all of the processes in main memory are blocked, and the operating system needs to bring in a new process, process D, which consists of 5 pages. Now suppose, as in this example, that there are not sufficient unused contiguous frames to hold the process. Does that prevent the operating system from loading D? The answer is no, because we can once again use the concept of logical address. A simple base address register will no longer suffice. Rather, the operating system maintains a page table for each process. The page table shows the frame location for each page of the process. Within the program, each logical address consists of a page number and an offset within the page. Recall that in the case of simple partition, a logical address is the location of a word relative to the beginning of the program. The processor translates that into a physical address. With paging, the logical to physical address translation is still done by processor hardware. Now, the processor must know how to access the page table of the current process. Presented with a logical address, page number, and offset, the processor uses the page table to produce a physical address of frame number and offset. Continuing our example, the 5 pages of process D are loaded into frames 4, 5, 6, 11, and 12. The figure here shows the various page tables at this time. A page table contains one entry for each page of the process, so that the table is easily indexed by the page number, which starts at page 0. Each page table entry contains the number of the frame in main memory, if any, that holds the corresponding page. In addition, the operating system maintains a single free frame list of all the frames in main memory that are currently unoccupied and available for pages. Thus we see that simple paging, as described here, is similar to fixed partitioning. The differences are that with paging, the partitions are rather small, a program may occupy more than one partition, and these partitions do not need to be contiguous. To make this paging scheme convenient, let us dictate that the page size, hence the frame size, must be a power of 2. With the use of a page size that is a power of 2, it is easy to demonstrate that the relative address, which is defined with reference to the origin of the program, and the logical address, expressed as a page number and offset, are the same. An example is shown in the slide. In this example, 16-bit addresses are used, and the page size is 1024 bytes, or 1 kilobyte. The relative address is 1502, which in binary form is 00000 10 111 0111110. With a page size of 1 kilobyte, an offset field of 10 bits is needed, leaving 6 bits for the page number. Thus, a program can consist of a maximum of 2 to the 6th, or 64 pages of 1024 bytes each. As figure B in the middle of the slide shows, relative address 1502 corresponds to an offset of 478, or 011101110 on page 1, which is 000001, which yields the same 16-bit number 0000001011110 0111110. The consequences of using a page size that is a power of 2 is twofold. First, the logical addressing scheme is transparent to the programmer, the assembler, and the linker. Each logical address of page number and offset of a program is identical to its relative address. Second, it is a relatively easy matter to implement a function in hardware to perform dynamic address translation at runtime. Consider an address of n plus m bits, where the leftmost n bits are the page number and the rightmost m bits are the offset. In our example in B of the figure, n equals 6 and m equals 10. The following steps are needed for address translation. Extract the page number as the leftmost n bits of the logical address. Use the page number as an index into the process page table to find the frame number k. The starting physical address of the frame is k times 2 sub m, and the physical address of the referenced byte is that number plus the offset. This physical address need not be calculated. It is easily constructed by appending the frame number to the offset. In our example, we have the logical address 00000011110, which is page 1, offset 478. Suppose that this page is residing in main memory frame 6, binary 000110. Then the physical address is frame 6, offset 478, 00011, 00111, 011110. To summarize, with simple paging, main memory is divided into many small, equal-sized frames. Each process is divided into frame-size pages. Smaller processes require fewer pages. Larger processes require more. When a process is brought in, all of its pages are loaded into available frames, and the page table is set up. This approach solves many of the problems inherent in partitioning. A user program can be subdivided using segmentation, in which the program and its associated data are divided into a number of segments. It is not required that all segments of all programs be of the same size, although there is a maximum segment length. As with paging, a logical address using segmentation consists of two parts, in this case a segment number and an offset. Because of the use of unequal size segments, segmentation is similar to dynamic partitioning. In the absence of an overlay scheme or the use of virtual memory, it would be required that all of a program's segments be loaded into memory for execution. The difference, compared to dynamic partitioning, is that with segmentation, a program may occupy more than one partition, and these partitions need not be contiguous. Segmentation eliminates internal fragmentation, but like dynamic partitioning, it suffers from external fragmentation. However, because a process is broken into a number of smaller pieces, the external fragmentation should be less. Whereas paging is invisible to the programmer, segmentation is usually visible and is provided as a convenience for organizing programs and data. Typically, the programmer or compiler will assign programs and data to different segments. For purposes of modular programming, the program or data may be further broken down into multiple segments. The principal inconvenience of this service is that the programmer must be aware of the maximum segment size limitation. Another consequence of unequal size segments is that there is no simple relationship between logical addresses and physical addresses. Analogous to paging, a simple segmentation scheme would make use of a segment table for each process and a list of free blocks of main memory. Each segment table entry would have to give the starting address in main memory of the corresponding segment. The entry should also provide the length of the segment to assure that invalid addresses are not used. When a process enters the running state, the address of its segment table is loaded into a special register used by the memory management hardware. Consider an address of n plus m bits, where the leftmost n bits are the segment number and the rightmost m bits are the offset. In our example before, n equals 4 and m equals 2. Thus, the maximum segment size is 2 to the 12th power, which is 4096. The following steps are needed for address translation. Extract the segment number as the leftmost n bits of the logical address. Use the segment number as an index into the process segment table to find the starting address of the segment. Compare the offset expressed in the rightmost m bits to the length of the segment. If the offset is greater than or equal to the length, the address is invalid. The desired physical address is the sum of the starting physical address of the segment plus the offset. Consider an address of n plus m bits, where the leftmost n bits are the segment number and the rightmost m bits are the offset. In our example in an earlier slide, n equals 4 and m equals 12. Thus, the maximum segment size is 2 to the 12th power, which is 4096. The following steps are needed for address translation. Extract the segment number as the leftmost n bits of the logical address. Use the segment number as an index into the process segment table to find the starting physical address of the segment. Compare the offset expressed in the rightmost m bits to the length of the segment. If the offset is equal, that is greater than or equal to the length, the address is invalid. The desired physical address is the sum of the starting address of the segment plus the offset. In our example, we have the logical address 000 1 0 0 1 0 1 1 1 1 0 0 0 0, which is segment 1, offset 752. Suppose that this segment is residing in main memory at a physical address 001 0 0 0 0 0 0 0 1 0 0 0 0 0. Then the physical address is 001 0 0 0 0 0 0 0 1 0 0 0 0 0 plus 001 0 1 1 1 1 0 0 0 0. To summarize, with simple segmentation, a process is divided into a number of segments that need not be of equal size. When the process is brought in, all of its segments are loaded into available regions of memory, and a segment table is set